Hello everyone. In this lecture, I'll be discussing the vibrational Raman spectroscopy and vibration rotation Raman spectroscopy. So far we had seen the rotation Raman. Now in this case, we'll see the transitions occurring in the vibrational energy levels in presence of the Raman effect. So let's take the example. Let's start with what we know about pure vibrational spectroscopy. So we know the vibrational energy levels are represented by V plus half h nu in case of simple harmonic oscillator, where nu is 1 by 2 pi under root k by mu. This is a vibration frequency, force constant, and reduced mass. Okay. What are the selection rules in pure vibrational spectroscopy? Delta V should be plus minus 1, and of course another selection rule, or the gross selection rule, is that there should be change in dipole moment at least during the vibrations or vibrational modes. If you consider the case of anharmonic oscillator, the energy levels are represented by V plus half h nu minus V plus half square h nu xc. Now don't confuse with the fact that why there is h nu. These are in joules. Okay. If this was in centimeter inverse, this h nu will not be there, only mu bar will be there. Now this is the anharmonic part. This is your anharmonicity constant or dissociation constant, because this is the part which is causing the anharmonic behavior of the molecule. Now in this case, the selection rule was plus minus 1, plus minus 2. It can do any kind of transitions, but mostly it was seen that delta V plus minus 2 and higher terms are not very much prominent. At least plus minus 2 is there, but not more than that. Okay. Okay, in this case, delta E was h nu, and in this case, delta E depends on what transition we are considering. For 0 to 1, what is also known as fundamental, delta E was mu E 1 minus 2 xc. This mu E is simply this one. Okay. Now, this is in centimeter inverse, that's why there is mu E. If this was in joules, this would have been h mu. For 0 to 2 or first overtone, we had delta E is equals to 2 mu E 1 minus 3 xc. And okay, let it be like this. Now, in presence of a Raman effect, that means when the molecule is present in a electric field and we are looking at the polarizability of the molecule because of its different normal modes, the changes that are going to occur in this case is that there will be an additional selection rule of 0. Okay. Why? They will see that. So there is only one big change, that there is an additional selection rule that delta V can be 0, both in case of simple harmonic oscillator and in case of anharmonic oscillator. Okay. So why would that be? Let's say this is your vibrational energy levels. The molecule absorbs some energy, does the transition, and again comes back to the same energy level where it started with. So in that case, V1 is equal to Vi is equals to Vf and delta V equals to 0. We had seen this is the case of Rayleigh lines. So delta V equals to 0 gives you Rayleigh line, or let's say the band center. Okay. Delta V equals to plus 1, let's say minus 2, minus 1, 0, plus 1, plus 2. This is your Q, P, O, R, S. So you'll get R, S, and further things. Okay. So in this case, what is going to happen? So I'm considering the case of anharmonic oscillator. What we are going to get is, let's say mu excitation is the energy which is provided, this one. So you will get, let's say, first Stokes line, mu excitation minus delta E. delta E is what? Let's say I'm considering first Stokes line will be for fundamental, so that would mean mu E 1 minus 2 xe. Second Stokes line will be mu excitation minus 2 mu E 1 minus 3 xe. If you are considering, okay, so why Stokes line? Stokes line because there is some absorption of energies occurring. Stokes lines always comes when the molecule absorbs some energy, and in case of vibrational energy levels, that energy is being absorbed to do the transition to some higher energy level. So that would mean the molecule goes here and let's say comes back only till here, not to the lowest energy level. In that case, there is a delta V of +1, right? So there is a positive transition in the vibrational energy levels, but in the Raman spectra, we will see the lines to be on the Stokes side. So how would this look like? The spectra will look like something like this. This is your mu excitation, delta V equals to 0, Rayleigh line. Okay. Now there will be line here. The intensities are going to decrease because you need more and more energy for the molecule to do transition from 0 to 2 as compared to 0 to 1. At the same time, 1 to 2, which is also known as hot band, as I discussed in my previous lectures, will have much less intensity compared to these. So this will be your 0 to 1, 0 to 2, 0 to 3, and further. Now, these lines are obviously R lines. If I'm not wrong, these are R lines and all lie on the Stokes side. At the same time, it's also possible to have lines on the anti-Stokes side. But their intensity is going to be less because less number of molecules are present at higher energy levels, which will do the transition to here and then come back to here for delta V equals to -1. So their intensity is going to be really less as compared to the Stokes line. This is what we had seen even in case of pure vibrational spectra. Delta V equals to -1 has really less intense peaks. That is the same thing is going to happen here also. Okay, but this is all about the formulas, all about the selection rules and all those things. But what is the concept behind it? How vibrations, whether be it symmetric stretch, it's asymmetric stretch or bending, influences the polarizability of the molecule to give these kind of spectra. We will take example of water and CO2, which by the way I have also discussed in my lecture on introductory lecture on pure Raman spectra. If you have watched that, you can skip this part. Otherwise, I am going to discuss the polarizability ellipsoids in water in its asymmetric, symmetric and bending modes. Same for CO2, and we'll see which modes are Raman active only, which modes are R active only, which are both active. And then we'll move on to the questions that have come previously. Okay, let's start with the example of water first. Water is a non-linear molecule, and by using 3n-6, we get 3 normal modes. First of which, let's start with symmetric stretch. So in case of symmetric stretch, water is going to stretch uniformly along all directions. Okay, so in this case, what is happening is the bond lengths are increasing. If the bond lengths are increasing, the electrons are going to be loosely bound in these bonds, and because of which their polarizability increases. If the polarizability along this direction of the bonds are increasing, the polarizability ellipsoid along these directions is going to become smaller. So in that case, if this had this will be slightly smaller, followed by this, which is much smaller. So there is a net change in the polarizability in its normal mode. So the molecule is going to be Raman active. And we know this is a IR active mode also because there is a permanent dipole moment. For asymmetric stretch, Now in this case, what is happening? The polarizability, or let's say one bond is getting stretched, another bond is getting shrinked. As a result, the polarizability is going to change. It does not matter that if this is changing by 10, the polarizability of this bond changes by 10 units, then this has also changed by 10 units. They are not same, and because of which there is a net change in polarizability of the molecule. In this case, also the polarizability or the polarization is changing in this direction, because of which it's going to remain the same. The extent of change is going to be different, but there is going to be net change in polarizability. That is why this is also Raman active mode and it is also an IR active mode. Finally, let's take bending mode. Now in case of bending mode, let's say we have this followed by this and finally this. Now, how do you see this? Let's say in this case, the polarization was much more higher because the bonds have much less repulsion. In that case, the electrons are loosely spread. So there is a bigger, you can say, change. You can say there is a good polarization in this case. While because of the bonds coming closer, the electrons are now shifting towards the oxygen, followed by this case in which the electrons are almost close to the oxygen. And if that is true, the polarization along this, let's say if this looks something like this, the polarization along this axis is going to decrease. That would mean the polarizability ellipsoid along this direction is going to increase. So this looks something like this, followed by this. Because the polarization along this axis has decreased, so there is an increase in the polarizability ellipsoid's length along that axis. In short, there is a change in polarizability. And if there is a change in polarizability, the molecule is going to be Raman active, while the bending mode is also IR active because of its permanent dipole moment. Now that was a simple case of a non-linear molecule which has a permanent dipole moment. Let's take CO2, which is linear. So it will have 3n minus 5, 4 normal modes: symmetric stretch, asymmetric stretch, and 2 bending modes, one in plane and one in out of plane. We'll start with the symmetric stretch. So we have let's say I'm doing the third one here. Okay. So in this case, what's going to happen is, since the same concept which you applied here, since there is a change in the bond lengths are going to increase, the electrons are loosely bound, and in that case they're more polarizable, so the polarizability along this direction increases. So the polarizability ellipsoid along this direction is going to shrink, or something like this. So there is a net change in polarizability, hence it is a Raman active mode. But if this is Raman active, we know this is IR inactive because there is no change in the dipole moment of the molecule. This is different from water. Let's take the example of asymmetric stretch. What do we have? This is an example of asymmetric stretch. In this case, what is happening? The polarizability along, so the polarizability along this axis is changing, but in this case, the polarization of this bond is higher. So what will happen is, the polarizability ellipsoid will look something like this. In this case, the polarizability ellipsoid has not changed its shape, but only the direction. In this case, the polarizability ellipsoid is simply like this. So that would have I gone wrong somewhere? I think so. Let's not make it direction based. So let's say the polarizable ellipsoid in this case is this. It remains same. It remains same here. That is because there is no net change in polarizability along this direction, because of which this is Raman inactive, but we know this is IR active, the asymmetric stretch. Finally, let's take a look at the bending mode. Now in case of bending mode, what do we have? We have this followed by this followed by this. Now in this case, this mode, the polarizability along this direction is higher. So in this case, the polarizability ellipsoid will look something like this, followed by this, followed by, in this case, between this mode and this mode, there is no change in the polarizability, because of which this mode is Raman inactive. So there is no net change in polarizability while going from this mode to this mode, even though there are two different orientations of the molecule. So that is why this is Raman inactive, but we know this is IR active. So the takeaway from here is that in case of non-linear molecules, when there is no point of symmetry, almost all of the modes are Raman active. But in molecules which have a point of symmetry, those modes which are IR active are not Raman active, and those modes which are IR inactive are Raman active. This is also known as the rule of mutual exclusion. And a number of questions have come specifically from rule of mutual exclusion, which we'll discuss in some time. Now let's take a look at the, fine. So I'm done with the vibrational Raman spectroscopy. Now we'll take a look at the combination of rotation, vibration, and Raman spectroscopy. So if we have understood the concept of rotational Raman and vibrational Raman spectroscopy, it is much more easier to come to the conclusion of vibration, rotation, Raman spectroscopy. So let's take a look at, we know the rotational energy levels are given by Vj, j+1, and delta E is 2b, j+1. Okay. Now in case of vibration energy levels, we have V plus half mu bar minus V plus half whole square mu E xc, and delta E is equals to mu E 1 minus 2 xc, considering only the fundamental mode of transition. Okay. So, and we know mu excitation is an energy which is supplied to the molecule for Raman spectroscopy. So in this case, what we'll get, let's take the example of Stokes line first. For Stokes line, first Stokes line will have mu excitation minus delta E. And what is delta E? Delta E is mu E 1 minus 2 xc plus 2b j+1. Okay, by the way, selection rules here is same as plus minus 1, plus minus 2, plus minus 3, considering, it is only plus minus 1, considering a diatomic molecule. We are not taking the case of polyatomic molecules now. For delta V, it is 0, plus minus 1, plus minus 2, etc. This, I think, also has the additional selection rule of 0, if I'm not wrong. Okay, now in this case, and if I open the brackets, I'll get mu E 1 minus 2 xc minus 2b j+1. Okay. Okay, let's not name it Stokes line. So let's say this is for delta V equals to plus 1, delta J equals to plus 1. But if we have delta V equals to plus 1, but delta J equals to minus 1, in that case, this will become right. So if I open the brackets, it's simply Okay, one more mistake I have done. This should have been plus minus 2. So if this is plus minus 2, this will become B4J plus 6. This will be B4J plus 6. Similarly, B4J plus 6, B4J plus 6, B4J plus 6. Okay, there will be a plus sign here. So how do you get the spectrum now? So if you have a spectrum in which, let's say, this is your mu excitation or Rayleigh line for delta V equals to 0. Now you have, let's forget we have the rotational part. You have the vibrational part, so you have mu e minus 2xe less than that. So let's say this is mu e minus 2xe, mu e 1 minus 2xe. Now there are rotational lines on the lower energy side of that and on the positive energy side of that. So lower energy side of that, these will be S lines and these will be O lines. So you have S lines here, you have O lines here. So that is different here. How in earlier case you had S lines on the first hand on the left side, O lines on the right side, but in this case both the lines are on the left side of the mu excitation, but with respect to the vibrational change, vibrational energy change, O lines are on the right side, S lines are on the left side. So this is important in the case of vibrational rotational spectroscopy. While considering the anti-Stokes line are going to be really weak, because anti-Stokes line will involve transitions 1 to 2, which are, let's say, the hot band, which occurs only at very high temperatures, not at room temperature. So at room temperature these are going to be really low, because the number of molecules in the first vibrational energy level is already very less. Okay. So that's all I wanted to discuss from, that's the only important part from vibrational rotational Raman spectroscopy. We'll now start with the questions that we have from vibrational Raman spectroscopy and vibration rotation Raman spectroscopy. Okay, so the first question we have is from net December 2017, and the question says the molecule is it 2017? I'm not so sure. The molecule that will show Raman spectrum but not IR spectrum. Now, for a molecule to show Raman spectrum but not IR spectrum, that should satisfy the rule of mutual exclusion. That should have a center of symmetry. The options you have H2, HCl, BRCl, and CS2. Now these are all let's say diatomic molecules. So in that case, we cannot say that this particular atom is a center of symmetry. This is equivalent to CO2, which we know has a center of symmetry and follows the rule of mutual exclusion. So the correct answer is option number D. The next question we have is from June 2012. The question says, for the vibrational Raman spectrum of a homonuclear diatomic molecule, the selection rule under harmonic approximation. Now what is the selection? We had seen in the case of harmonic approximation, the delta V equals to 0 plus minus 1, which is your option number D. A very straightforward question. The next question we have is from December 2012. And the question says, in the vibrational spectrum of CO2, the number of fundamental vibrational modes common in both infrared and Raman. Now CO2 follows the rule of mutual exclusion. So there will be no mode which is common or which is active in both or inactive in both. So the answer for this is 0, which is given in your option number D. Okay. The next question we have is from December 2016. The question says, among the following, both microwave and rotational Raman active molecule is. Okay, for a molecule to be both microwave and rotational Raman active, what do we have? CH4. Now this question should not have been a part of this lecture, but I'm still going to discuss it because I missed it on the last lecture. CH4 is spherically symmetric. There is no change in the polarizability. N2O okay, then we have C2H4, then we have CO2. Now, I mean, all of them are rotationally active, but all of them are microwave active, but rotation Raman active and microwave active. So this is obviously not. CO2 is rotation Raman active, is not going to be rotation Raman active. N2O, okay. Let's say in this sense, there is no change, there is no permanent dipole moment in this and this, but there is a very good permanent dipole moment in this, because of which this molecule is Raman inactive, this molecule is rotational inactive, this molecule is rotational inactive, this molecule rotational inactive, but this is going to be rotational active, and it is also going to be rotational Raman active. So this is the answer which is given in option number B. Then next question we have is from December 2017, and the question says the normal mode of ethylene represented by the figure below. So in the figure you can see the hydrogen atoms are bending. Now in this case there is no change in the dipole moment of the molecule. So the dipole moment remains same, so that would mean this is an IR inactive mode. And if you see, there is a center of symmetry between the two carbon-carbon bonds at the middle of the carbon-carbon bonds. So how do you find? You have this. If you start from here and go straight, you are going to reach the exact same atom on the other side. So this is the center of symmetry. That means it follows the rule of mutual exclusion. That would mean if there is an IR active mode, it's going to be Raman inactive. In this case, this is a IR inactive mode because there is no net change in the dipole moment. So it's going to be Raman active, which is given in your option number B. Okay. So that's all the questions from NET. Questions from GATE, there are none. Now let's take a look at TIFR. So the first question we have is from TIFR 2012. The vibrational Raman effect, a considerably weak scattering phenomenon, was first reported by late Sir C.V. Raman in 1928. The intensity of individual vibrational resonances observed in Raman spectrum is proportional to. Okay, so the intensity is proportional to number of molecules. Yes. Polarizability of the bond. Obviously, we had seen that in case of the transition moment integral, the polarizability, a change in polarizability comes out of the transition moment integral, and it is actually affecting the intensity. The higher the molecule is polarizable, the more is the intensity of the peak. Thirdly, wavelength of radiation used. Obviously, it's going to be affect because we are giving h nu, and h nu is hc by lambda. So the lambda is also going to affect the intensity of the peak. So all of them affect the intensity of the vibrational Raman peaks. Okay, so the next and the last question we have, I think I have missed one question. No. Okay, so the last question we have is from TIFR 18, and the question says, suppose you are carrying out an experiment measuring the Raman spectrum of N2 gas in the outdoor air. Where would you find the higher strength of the anti-Stokes line? Anti-Stokes line means from higher energy level to lower energy level. That means more number of molecules should be present at higher energy level. For that, you need higher temperature. What are the options? In Kanyakumari, on top of Mount Everest, the strength will be same in both the places. Nitrogen would not have any anti-Stokes Raman line. So last option is obviously wrong. The strength is going to be same? No, it depends on temperature. On the top of Mount Everest, temperature is very low. You will not have many molecules at the higher energy level. But in Kanyakumari, the temperature is higher, so you are going to have more number of molecules at the higher energy level. So you will find more intense anti-Stokes line. So the answer is option number A. So that's all the questions we had for vibrational Raman spectra and vibrational rotational Raman spectra. So by this we have come to the end of Raman spectroscopy. In the next lecture, I'm going to discuss different aspect of vibrational spectroscopy. We'll study vibrational spectra of spherical molecules, how some molecules are able to produce plane polarized light. We'll see that in the next lecture, and then in the next, the upcoming lecture after that, we'll start with the electronic spectroscopy, and with that we'll be able to complete or finish the discussion on molecular spectroscopy.